We can start then.
Thank you.
Dear participants, dear colleagues, it's a great pleasure for us to introduce our today's speaker, Professor Juan Bartolome. Let me say a few words about his scientific career. Professor Bartolome received his PhD in 2075 at the University of Saragossa, Spain, followed by a postdoctoral stay at the Kamerlingh-Ons Laboratorium of the University of Leiden, Netherlands. In 1986, he was appointed as a research professor by the CSIC, this is Institute of Nanosciences and Materials. His research interests are related to phase transitions in solids, permanent magnets, new phases and phenomena, molecular magnets in particular, and their quantum behavior. He has been a frequent user of neutron and synchrotron facilities in Europe. Professor Bartolome served as a scientific counselor of Aragon regional government. He was member of panel of new materials of Spanish Ministry of Industry, director of European Laboratory, Mainz, Grenoble, Saragossa, and industrial coordinator of CSIC in Aragon. In 2016, he was elected as a member of Royal Academy of Sciences of Saragossa in physics section. Besides the ESRF Synchrotron, which is located in Grenoble, France, he acted as scientific counselor, member of Administration Council and Scientific Advisory Committee. He participated at the Scientific Advisory Committee, in particular in the Soleil Synchrotron in Paris, France. He has been a member of International Scientific Committee of Solid Compounds of Transition Metals since 2010 to his retirement in 2018. He chaired this solid compounds and transition metals meeting in Saragossa in 2016. He is cooperating with, and this is especially pleasant to say, he is cooperating with the Working Institute of Low Temperature Physics and Engineering since 2008. During his career, he has received the award of the Domenico Martinez Foundation and the Magnetism Prize Salvador Velayes of the Spanish Magnetism Club. Dr. Bartolome has published over 400 indexed papers and supervised 17 PhD theses. His today's talk is devoted to X-ray magnetic circular Dichroism and its contributions to condensed matter magnetism. This is very actively and rapidly developing field, and we are excited to learn more about it. And please, Professor Bartolome, the floor is yours.
Доброго дня. Я хотів би подякувати колегам із Верхній інститут за можливість зробити цю презентацію. So, good afternoon. I would like to thank my colleagues at the Working Institute of Kharkiv the opportunity to address this presentation to the Kharkiv Quantum Seminar, and especially to my good friend Valentina Sirenko, and in remembrance to our common friend Professor Eremenko. Now, as you said, my talk is devoted to X-ray magnetic circular dichroism, and in the second part, its contributions from our side to condensed matter magnetism. The reason to choose this talk is because of the extreme breakthrough that this technique has produced from the experimental point of view into magnetism. Actually, synchrotron radiation is produced in nature by electric charges moving at relativistic speeds in a magnetic field. We can see here an image on the synchrotron radiation produced by a stellar explosion at the Messier 82 galaxy, or else by ultra-relativistic electrons traversing the Jupiter's radiation, Jupiter's magnetic field. Now, in the Earth's surface, we have artificial synchrotron first observed directly in this historical photograph at the Betatron in Schenectady in 1947. Here you can see the light shining through the porthole of this ancient machine. Of course, since then, synchrotrons have evolved strongly. Nowadays, there are 50 machines in the world. 30 of them are third-generation machines. And I shall focus then only on our main sources of synchrotron for Spanish users. The first is the European Synchrotron Radiation Facility, which is in Grenoble. It's a 6 giga electron volt machine. And since 1986, we have been involved into the construction and operation of this important synchrotron facility. It is now being upgraded to an extreme brilliance source. But later on in 2012, since then we have our own Spanish synchrotron at Alba. I say Spanish, but it is open to any users, of course, and where it houses now 13 beam lines. Of this, I want to mention the Boreas beam line, which is a soft X-ray beam line with a photon range from 80 to 4,000 electron volt. Temperature ranges from 3.4 to 300 Kelvin, and it has got at the end station a magnetic field up to 6 Tesla with a superconducting coil. Now you see here a photograph of the beam line where at the end is the cryostat with the magnet and the position for the sample. I shall introduce now some of the components of this type of synchrotrons, which purpose is the production of intense X-ray beams collimated of minimal transverse cross-section. The electrons are produced by thermoemission, introduced in a linear accelerator, then in a booster that introduces the electrons into the closed loop of the storage ring in the synchrotron. This closed circuit is managed by the so-called bending magnets, some control devices, and the loss of energy is compensated by radio frequency cavity. Very important are in the linear sections, we have the so-called insertion devices, of which I shall speak about in more detail in a few minutes. Now, in general, not always, but in general, these electrons, when traveling in the bending magnets, they produce a very thin cone of synchrotron light, which then travels as a lighthouse. Indeed, since the electrons travel in this loop as packets, at the end station, we actually observe the light shining with a time structure. The energy of the emerging photons covers a wide domain, indeed. Now, I go to more detail into the light that emerges. When it is coming from a bending magnet, the light is polarized linearly in the equatorial plane of the synchrotron, and then above and below we can obtain circularly polarized light to the right or to the left, depending if we observe it above or below this equatorial plane. But for us, more important are the so-called undulators. Undulators are pieces of machine, the insertion devices, which consist of a collection of permanent magnets, so that when the electron beam enters, it wiggles within the permanent magnets, and each time we have a wiggle because we have an acceleration, centripetal acceleration. Photons are shown in the forward direction. And this is very interesting because electrons are traveling at relativistic speeds, so very near to the light, to the speed of light. They see this piece of equipment, which can be several meters long, as a diffraction grid because of the relativistic length contraction as seen by the electrons of this undulator. So the light that goes in, that is shown from the different wiggles into the front line, have constructive interferences. Therefore, we can have a very intense very intense X-ray beam. As we move the different parts from one respect to the other, we can actually obtain polarized light or circularly polarized light to the right or to the left. So we have an ideal element to obtain the light we need for our XMCD experiments. Now, the light that goes out of the insertion device is has got multi-wave lengths. So very often we just need one wavelength. In that case, we set in a beam line a monochromator, whether by double mirrors or grids, to obtain the monochromatic light, which is collimated, impinges on the sample, and then the photon or photoelectron that is emitted will be detected by the adequate detectors. Now, the basic experiment on which all this technique is hangs on is the X-ray absorption spectroscopy. SAS, in short, is the way how atoms absorb photons, and it lets it transitions from the core created hole to the available empty states at higher energy that may be allowed by electric dipolar or quadrupolar selection rules. Now, when the light shown coincides with the energy of one of the shells in the atom, we get a strong peak, a sharp peak, which we name as absorption edge. Depending on which shell we are hitting, because we shall use it later in the talk, we name it as K edge, which is the 1s level, or L23 edges, when it is the 2p, or M45, when this is the 3d. So the 1s, the 2s, the 2p, or the M lines. So these energies are actually dependent on the element, and they are dependent on the surrounding. So we have here a technique which is allows to have a fingerprint of the atom which is being studied. So it is element selective, but it is also sensitive to the crystal field, chemical coordination, site symmetry, and oxidation state. Here we have an example on iron, the SAS of iron, where we see 3 cases with the state of valence different. So it's 0, 2, and 3. You can see clearly that there are shifts in the edge energy and different structures that allow us to use it as a fingerprint technique. Now, this SAS technique can be performed in what we call the soft X-ray range, so at lower energy, photon energy. These photons have to be kept, so the experiment has to be done at high vacuum because of a scattering of air. And usually we get very strong absorptions due to the dipolar transition dipolar transition probability. Now, it covers the 3D metal L2-3 edges, which is very important in magnetism since we are then populating the 3D states or bands from where the transition metal magnetism stems, or also on lanthanides at the M4F edge, because we are populating the 4F edge of these elements. You can see here an experimental result on the ferrite, where at the iron L2-3 edges of a ferrite, where these are depending on the amount of nickel that has been substituted. So you can see clearly that there are different behaviors. But it can also be done at higher photon energy, art X-rays, and then the typical absorption spectra can be separated in two regions, the so-called SAINS, which is X-ray absorption near edge structure, this region, where we get information on the oxidation state or D-band occupancy, or else above this wobbly region is the so-called X-axis region, extended X-ray absorption fine structure, where it is sensitive to the local chemical environment surrounding the absorbing atom. So we can get information on coordination number, the bi-Wöhler factor, or potential corrections. Well, we have here an example of titanium perovskite of lead, where you can see the dependence of the absorption as a function of temperature, and is compared to a titanium oxide, where you can see clearly the differences that can be studied. But then we come to the X-ray magnetic circular dichroism experiment, which is based on the X-axis technique. The experiment is as follows. From the insertion device, we have got a beam of photons circularly polarized to the right or to the left, and a magnetic field which is parallel to the beam, impinging then on a sample which is on a turning table. We can orient this turning table in any direction. So the photons emitted will be then detected by the adequate detectors around. Now, to illustrate this technique, I shall make use of the experiment at the L2-3 edge of a transition metal. The magnetism of a transition metal in a field can be explained in terms of its 3D band split into a majority spin down and minority spin up subbands below the Fermi energy, and the complementary empty subbands above it. Besides, the 2p shell, which is a spin orbit coupled split, has to be taken into account to understand the process. So if we shine light with the light helicity vector parallel to the 2p orbital moment, for example, at the L3 for electron, it will be excited to the corresponding whole subband of the up spin orbitals. The same, but for left circularly light, it will excite the electron with the down orbital moment to the upper whole subband. How does this show up in the experiment? The first process, the L3, as we scan through this photon energy, it will show as a peak around the edge value. And in the second case, with the left circularly polarized light, it shows as a lower peak. So The difference between the two peaks is precisely the XMCD signal, in this case for the L3 band. Of course, we do the same in the energy region corresponding to the L2 excitations from here to the hole, and we see again in the absorption 2 peaks, although reversed in magnitude. So in this case, the difference is positive. The average between the two is the absorption. So this is the basics of the XMCD experiment at the L23 edge. It would be not so important unless we mention now the so-called sum rules. The sum rules have given the potential to this technique in magnetism. That's why it is so important from then on. We deal now with the integration of the absorption signal once we have we have taken out the contribution to the transitions to the continuum. So this area is proportional to the number of holes, which allows us to normalize whatever we observe per atom. So we are getting information always per atom on the average that has been measured. Now, when we do the L3 measurement, so the difference between the up and down polarizations, this intensity is proportional to L plus S since it comes from the L plus S orbital, 2p orbital. But if we perform the L2, it is proportional to L minus S. So by adequate mathematical operation, we can obtain that this combination A minus 2b gives a magnitude of the so-called effective spin moment, while by the addition, it is proportional to the orbital moment. So, alas, we have got a technique which is capable of separating or distinguishing the orbital moment from the spin moment. This was something not achieved till this technique was available. How to measure these magnitudes is simple once the experiment has been done. We only have to integrate the absorption once the continuum has been subtracted to obtain the so-called parameter R, and integrate the XMCD region up to the middle point between the two L2 and L3 edges and up to the total XMCD signal, which are called P and Q parameters. Then Tole and Kara obtained these expressions, which are of paramount importance, where we can simply substitute P, Q, and the number of holes to obtain the orbital moment and the effective spin moment. I mentioned effective spin moment because it has got two components. It has the actual spin moment and second part, which is the dipole magnetic moment of the spin density distribution, which can be calculated or can be neglected in many cases by symmetry considerations. So we have a simple method to obtain these important parameters. Now, to get a more easy to understand grip of what we are measuring, let's consider a sample where we have a magnetization M, and then we apply field and shine the synchrotron radiation along the field direction of the field. Then what we are measuring is the projection of the magnetization, so this, of the magnetization into the direction of the field. That is the scalar product of M times H divided by H. since we can orient the sample at will, then we can measure the different components of the total magnetization, which we explain here as a much function of the angle of incidence. So then, if we are interested to measure the evolution of the magnetization, since the height of the peak is proportional to the difference of number of holes, it is proportional to the total magnetization. Then we fix the energy at one value of the minimum or a maximum in the XMCD signal, and then we performed different experiments at different fields. By this scanning, we can measure the dependence of the magnetization as a function of field. Okay, so we have a technique which is now element selective, valence selective, site selective, surface sensitive. You can separate orbital, spin, and also measure the total magnetic moments, angular dependence. You can measure as a function of applied field and vary temperature. And I shall also speak about imaging with XMCD, which is called the technique X-PEEM. I shall not talk about time-resolved XMCD, since I have not direct experience in that. The type of systems that may profit of this type of studies is enormous. It goes from thin films to molecular magnets to magnetic oxides, name it. Okay. So far, so good for the introduction to the XMCD experiments. Now I shall try to gloss this information with experiments obtained in our lab on magnetic systems. Well, we know that magnetic systems nowadays are all around and are of uppermost importance. Since the compass was invented probably by Chinese, permanent magnets have been very important in our daily life. Now, we shall use the potential of the XMCD technique because of its orbital spin moment separation and element selectivity and angle dependence in the first example I want to show you. This is a neodymium 2 iron 14 boron, which is the magnet nowadays of highest power performance. The material consists of two sublattices, the iron sublattice, which is metallic, and creates a very large magnetic moment. And the neodymium sublattice, which has uniaxial anisotropy and gives to the whole sample a powerful collinear magnetization, which is the reason why it is so powerful. So below 588 Kelvin, you see here the magnetization, which remains down to 135 Kelvin, where the properties deteriorate. They deteriorate because the system is not, the two sublattices are not anymore collinear. They are not oriented in the same direction. To prove this, what we did is design an experiment where the sample with its permanent magnet EC axis is shown here by this vector, and we applied the field and performed the XMCD experiment, and then obtained the information of done at a certain KH, for example, iron, above the spin reorientation transition. But when we pull down below, you see that the projection varies below the transition. So as said, above the transition, below the transition. So you can see the variation in the projection of the magnetization. This you can see here in the experimental results as measured on the neodymium L2H and on the iron KH. In both cases, you see that at the spin reorientation transition, we get a non-zero, so we get an excess in signal, which is the difference between the two projections. This was actually the first observation of a spin reorientation transition with XMCD. But we have been using the element selectivity of the technique so far. But then we performed a new experiment on the L2, L3 edges of iron, and we could vary temperature and go through the spin reorientation transition and detected that the orbital moment, so here we are using the separation between the spin and orbital moment, had a very strong critical behavior, so a strong upwards increase in the orbital moment, which, by the way, can be associated to the derivative of the spin reorientation transition angle with temperature. And this was completely unexpected again. And we could explain it as due to the coupling of the structural transition that takes place precisely at the spin reorientation transition with orbital moment. So let's change of type of systems, and we go now into nanomagnetism. We use the two possibilities that I just mentioned, but now, because of the smallness of samples, we are profiting of the very high sensitivity of the technique. We have done a thorough study on anisotropic nanoparticles, which have been are being used as memory devices for bits. Now, its use is based on the existence of two orientations in the magnetization of the particle, which can be correlated to up and down, which are stable in temperature and are separated by a barrier which is proportional to its volume and to the so-called anisotropy constant. Of course, to maximize the density of memory elements, we want to reduce the volume of the particles, and then we need to increase the anisotropy, of course. This game has been very effective, and there has been an increase, doubling the density almost per year. That's called the Moore's law. But this game has got a limit. The bit can only operate below what's called the blocking temperature, because above it, the system behaves paramagnetically, and so the system does not hold a magnetic stable orientation. So this is the sort of particles we are interested in, although we chose particles of cobalt, which are not so interesting from the point of view of technology, because they have their blocking temperature quite low. But they are very interesting toy nanoparticles because they allowed us to say a number of tricks with the matrices where they were sitting. The particles were produced by subsequent deposition by sputtering of amorphous alumina, then cobalt, then they self-organized into spheres of a diameter that depended on the time of sputtering. Then we could cap them with different metals. I shall be speaking of copper, silver, and gold, and others. And then we can proceed sequentially to obtain up to 25 layers. Each of these cobalt particle crystallizes in the FCC structure, as you can see here from electronic microscopy. And they organize within the layer in hexagonal path with the next layer shifted so that the upperward atom would fall in the hole of the lower sheet. We can see here electron microscopy sections of these materials. Here you see the multi-layer. Here you see enhanced the cobalt particle and the copper. In this copper, in the case of copper cupping, which surrounds the particle and also connects one particle to the other. And they are separated one sheet from the other by the so-called alumina spacers. So you see here the magnetic susceptibility of these cobalt particles for 1.8 nanometer diameter. The blocking temperature is relatively low, so it's about 12 Kelvin. Now, as we cap it with copper, silver, or gold, you can see that the blocking temperature increases. We did also magnetic experiments, where we varied the average diameter of the particles. And we could fit this dependence with the expression Kf equal a K bulk, which is that for cobalt, plus a term which is linear dependent of the anisotropy at the surface divided by the average diameter. So the smaller the diameter, the larger the effective anisotropy. And for fixed diameter, you can see an increase in the anisotropy in the trend where cobalt, copper, silver, gold, cupping. So it's clear that we have this trend in the anisotropy increase. And that the reason is that there's some interaction between the surface of the cobalt with the matrix that is in contact with the cobalt particle. So we made, in order to try to understand better this phenomena, we made an XMCD experiment where we see at the L23 edges of cobalt, where we see that there is an increase in the raw XMCD signal at the L3 edge that once analyzed in terms of the orbital moment could be correlated linearly with the increase of effective anisotropy. So it is clear that the increase in Kf is related to an increase of the orbital moment of the cobalt atoms at the surface of the particles. To understand better what was happening at this surface, we then did study the XMCD at the cupping metal different elements. So here I show you the results for the gold cupping. So we have got gold around the central cobalt particle. And when we measured as a function of field, naturally, at 1 Tesla and 5 Kelvin, we did observe clearly an XMCD signal at the gold L2 and L3 edges. So this means that we have magnetic moment in gold. This could be understood considering that there may be hybridization between the 3D and the 5D of the cobalt and the 5D band in gold. we did this systematically for all the substitutions, and we could find that this hybridation exists in all cases, and it can be seen that they go in the trend 3D copper 3-4, the silver 5D gold. So the ND electrons from the different cupping metals are shifted to the cobalt 3D, and then we have an uncompensation between the spin up and spin down 5D subbands, which give rise to the non-zero magnetization at the cupping shell. Okay. But then we sputtered tungsten. This is very different because tungsten has got a 5D4 band in the metallic state. Then tungsten enters into the particles. It doesn't remain at the surface. They enter and substitute several cobalt atoms so that the number of neighbors of each cobalt is now different. We get then amorphous nanoparticles, but anisotropic. The anisotropy of them is due to a short range order within the cobalt atoms within the particle. I'm not going into those details, but I want to show this case because since the tungsten is a 5D4 electron band, so it is less than half filled, the prediction is that when there is and it supports magnetism, ML and MS should be antiparallel. However, when we measured on our particles and also on the cobalt-3 tungsten alloy, we observed that ML and did the sum rules analysis, we observed that the ML is parallel to MS. So we are violating the third Hans rule, so it is not fulfilled. This was quite unexpected, although it's not the only case that is in the literature. But in our case, we could correlate this with the effect caused by the decrease in the interatomic distances when cobalt is alloyed with tungsten. Yet another example is when we sputtered platinum or palladium. Platinum or palladium have got D9 bands, so they support magnetism. What's interesting is that, contrarily to the previous case, now these cobalt platinum alloys, cobalt platinum or cobalt palladium alloys in the L10 space structure, so they crystallize pretty well, and they show a perpendicular anisotropy respect to the substrate where they are deposited. This is very interesting because by using perpendicular anisotropy, we can get more dense memory supporting systems. So very different to what we have been so far. Platinum and cobalt, both magnetic active, actually below a certain temperature orient themselves in ferromagnetic way, and below a certain temperature, which are about 150 Kelvin, they are hard ferromagnet oriented. We could prove this by measuring at the XMCD of L3H and at the XMCD of the cobalt KH, and we see that both experiments coincide in coercive force, so we can we are showing that both are collinear in this range of temperature, and they support a strong hysteresis curve, which coincides with the results obtained from squid magnetism on the actual macroscopic macroscopic surface. Moreover, we did KH measurements of our samples, which is this, and compare it to the bare cobalt particle or to the cobalt platinum L1 structure. And we see that it is in between. What does this mean? This means is that besides having the cobalt platinum structure, there is still bare cobalt. So we think that these particles are of the type of core shell. So a core of cobalt remaining and a shell of cobalt platinum or cobalt palladium material. So far, so good. We have made use of the element selective of the orbital spin and the spin anisotropy on very small samples. But then we shift to another type of problem. Now we stay with gold, only gold. And then we could deposit nanoparticles of gold on a so-called S layer of an archeon, which is the sulfologous ácido calcareous archeon. These particles attach to this surface by means of sulfur dangling bonds. And to our surprise, when we measured the XMCD of this material, we could see a very strong signal at the L2-3 edges of gold, which means that this gold is magnetic, of course, under a field. When we measured the field variation, we could see that there was a paramagnetic dependence, which proved that this was really magnetic gold. The sulfur atoms we could prove that have a very strong influence on this magnetism, because when we used an archeon which had not the sulfur dangling bonds, the magnetism actually disappeared. So we could rationalize this behavior as due that the gold is losing some electrons towards the sulfur, and then we have got again an uncompensation between the spin up and spin down bands, which give rise under the field to an induced magnetic moment. We still did some more experiments on clusters. Platinum clusters now can form well-packed clusters that can be embedded into zeolites. In this case, I'm showing is sodium Y zeolite. These clusters are strongly packed, and we were wondering whether they would support also magnetism. Indeed, we measured the XMCD signal at 7 Kelvin and 6 Tesla of platinum, and as a function of field, we could observe that it was also behaving in a paramagnetic way with field. But very curiously, when we did quantitative analysis of our data, we found that the signal we were obtaining in this case was very small. So we had to go to theoretical calculations performed with DFT and FDMNS to show that only a fraction of these particles are giving a magnetic moment. And we conjectured that basically it is they are due to the so-called FCC crystallization case. Okay. We go on to what's now very interesting from the point of view of materials. In molecular magnetism, they're interesting because they provide contrast materials, sensors, and they are searched as qubits, and because they can, we can think of these materials as growing nanoparticles from bottom-up method. Besides what we have been explaining up till now, these systems have got a special problem. It is that they contain carbon and hydrogen atoms, and they have weak links in these hydrocarbons. So radiation damage can be a real problem in this type of studies. There have been techniques already developed to cope with this difficulty, of course. The first example I want to show you is what we call the butterfly molecules of iron-3 lanthanum oxide. Why butterfly? Well, the three atoms, which are iron-3, are in a triangle, and in vertical to it, in the so-called body of the butterfly, is located the lanthanum atom. The rest of the molecule provides the wings of the butterfly. So we measured its magnetic behavior and found for the, I'm showing here the case of dysprosium substitution, we found from a squid the magnetization behavior of this molecule as a function of field up to 14 Tesla. And then we were interested in understanding the interaction between the lanthanide and the iron sublattice. So we performed L2, L3 XMCD measurements on the dysprosium element, and we can see clearly excellent signals, which now cannot be analyzed in terms of some rules. However, we could measure as a function of field at the top of one of the edges, at the L3 edge, and we found paramagnetic behavior. With these measurements, we could then go to our total spin. Here is represented the dysprosium signal, and from the difference, we could extract the information of the behavior with field of the iron-3 sublattice. Of course, one can think, why not measure directly at the iron-2,3 edges of iron, for example? Because we collapsed against the radiation damage problem. So we did the experiment, but it was not successful. However, from this difference, we could obtain the iron sublattice behavior. Here I show you a comparison where these results are collected. In the case of yttrium, which is non-magnetic, which gives then the behavior of the pure iron triangle compared to the Brillouin zone, to the Brillouin function prediction. And then we made the different substitutions of terbium or holmium dysprosium, and we see that they were increasingly lowering its value, which means that the interaction in all cases is anti-ferromagnetic. Next case I want to show you is iron 2 in the phthalocyanide molecule. This is a very planar molecule which can be grown on a substrate, in this case is gold, with MgE, creating a pseudo crystal of molecules parallel to each other at a certain angle. And then we perform the L2-3 experiments on this sample where we could rotate it in the experiment. So this is the incoming light and parallel field at all instances. And we can see here the L3 signal. You can note that this is very rich in fine structure. This is because the magnetism of this atom is atom-like, not as metal as we have seen in the cobalt or other particles. And you can see how they vary with Anton. Now, from the some rules analysis of the signals, we could determine that the orbital moment and the effective spin moment increased when the incident angle was near recent incidence. That is, we could prove that this the magnetism of these phthalocyanide particles has planar anisotropy. And what's also very interesting is that we observed an orbital moment in the plane which is very high, which is clearly unquenched orbital moment, which was quite unexpected. So this is to illustrate the capacity of the technique with angle dependence and very small signals from very thin layers. This is a extreme case. Also, iron phthalocyanine molecules, but just one only layer on top of silver. This is made. This image is made with a stem, so tunneling microscopy, and then at low temperature we could put some oxygen on top, and the molecules would reorient and change its electronic state. So you see here the XMCD measurements done on these systems. This one corresponds to the monolayer here, and this one corresponds to the oxidated layer, identical layer. You can see clearly that there is an increase in the magnetic moment, but by more than an order of magnitude. What is also very curious is that when we take away the oxygen, we obtain back more or less the same magnetic state as at the beginning. So this is a reversible process. You can see here actually a magnetic switch, which is driven by the presence of oxygen. These are the angle dependence where we have seen exactly the same. Now, the black line is the calculation of an iron 3 case. So we could then rationalize our observation by certain calculations where we could assume that this oxygen enters in between the phthalocyanine molecule and the silver substrate. It pushes down the iron atom, and moreover, it modifies its surrounding. So we go from fourfold quasi-planar coordination to a pyramidal coordination with different charges around. So we have rationalized this with some calculations, saying that when this oxygen enters here and this happens, the system goes from the iron 2 state to the iron 3, and iron 3 is capable of sustaining a large magnetic moment. Fine. Next example is completely different. We are dealing here with chromium wheel molecules. Chromium wheel molecules. Why are they interesting? Well, they are good study systems to study coherence within the wheel, but they can also provide good qubit candidates. For example, in this case, one of these chromiums was substituted by nickel and gave a qubit with a spin 1/2. But this is a low spin, so we were interested in finding examples with a higher spin. So we came across to an experimental study of the family of chromium-10 systems, where they were also organizing themselves. The chromiums were organizing in a wheel. Then, in the case where R is methyl, we found in the literature that there was an upper increase in the susceptibility, which was later interpreted by EPR measurements, that there was an anisotropy, uniaxial anisotropy, perpendicular to the plane of the wheel, and with a spin 9. This spin 9 is very interesting because it's not zero, but it also implies that it has got ferromagnetic couplings, because in antiferromagnetic couplings would give us a spin 0. Totally ferromagnetic coupling would give us 15 in spin. So we thought it was worthwhile to do a deep study, which we did on magnetometry, heat capacity, XMCD, inelastic neutron scattering, and compared it with calculations. We did the XMCD experiments at the chromium K edge, and we found that from that point of view, all chromiums were identical, chromium 3. And by climbing up to 16 Tesla, we found that the molecule was not reaching magnetic saturation indeed. It could go up to 25. Then by ab initio DFT calculations, we could explain the anisotropy as due to the sum of each chromium anisotropy, which were proven that their axis was nearly the parallel to the vertical axis. And by model calculations by Monte Carlo, we could explain this magnetism as due to the molecule separating in two wings, ferromagnetic coupled chromiums at one side, and at the other side separated by an antiferromagnetic coupled chromium up and down. Indeed, we could explain the magnetometry, susceptibility, magnetization, and inelastic neutron scattering with that technique. And at very low temperature, we could prove that this molecule behaved as a spin molecular magnet, as we were expecting. Now, since this is a very robust molecule, it could be deposited on a surface. In this case, we did two cases on gold, on copper. And you can see here how these molecules sit on one or the other surface. So we did XMCD measurements on the chromium, on the 1 monolayer copper, 1 monolayer gold, and 14 monolayer on gold. We could see not really clear differences, but when we measured as a function of field, we observed that the layers, the monolayers were having a very different behavior, lower behavior, than the 14 layer and than the bulk one. So we did some more calculations and found out that we could explain this change by an evolution of the couplings of the within the wheel to spin 6 and spin 3. So this is one of our latest experimental results in the group. I shall go on now to my last case, is to show you the potential of this technique in microscopy. The technique is called X-PEEM for X-ray photoemission electron microscopy. The experiment consists in on a sample shining X-rays polarized either to the right or to the left on the sample where there's an applied field parallel to it. So the XMCD process takes place. The X-rays takes place, and the electrons, secondary electrons emitted, are put into a electron microscopy column, which then allows to image the surface which has been bombarded by X-rays. We can do that for the two polarizations and then calculate the differences. And you can see here the result. You can study you can see the presence of magnetic domains, different magnetic domains within the surface of the material. This is what our technique is sensitive to. To illustrate this, I show you here a study on thin cobalt films where we have perforated these films with holes. So we are having here the so-called anti-dot material. And we have been varying the distance between holes till the distance was so small that practically the only material that remained was that between the holes. So we performed the experiment, and you can see here up down to about 150 nanometers in distance that appear these magnetic domains, which are called super domains since they encompass several arrays of holes, and they are anchored to these holes clearly. And then the coercive force, the coercive field increases up to a certain value, where from then on they don't remain in columns, but they spread out through the 2D surface of the thin film. Eventually, the coercive force decreases because it finds new ways to separate themselves until we come to the asteroid-like remaining material between the holes, which will then behave as a particle. So we change over from the super domains spread to the particle-like behavior. So I have been trying to illustrate in this talk what this XMCD is important, why it can be considered that it gives a breakthrough magnetism, because it's element selective. It resolves orbital from spin magnetic components. It provides angular dependence, very high sensitivity, allows to study plethora of different systems, and we can use it for X-PEEM imaging. The examples I have shown were permanent magnets, nanomagnets, molecular magnets, and imaging in antidotes. I want to mention by name those persons who have been working on this subject very closely at our institute: Fernando Luis, Fernando Bartolome, Luis Miguel García Vinuesa, Javier Rubin, Julia Herrera Villas, Laura Badías, Ana Arauzo, and Javier Luzón. And also in Barcelona, Elena Bartolome, Adriana Figueroa, Xavier Batlle, and Labarta. And it would be too long to name all of them, but you see they're spread over the world. The synchrotron facilities that we have used have been essentially the ESRF at Grenoble, Photon Factory in Tsukuba in Japan, BESI in Germany, and ALBA in Spain. Well, thank you for your patience, and Yakuyu. That's it.
Professor Bartolome. So we are now entering the questions and answers session. So please. Do we have questions from audience? Yeah, I see from Yuri Skripnik. Please unmute your microphone if you have.
Oh, thank you. So, Professor Bartolome, you started your nice talk with mentioning substitutional alloy, and then you followed and showed a system which can be disordered or ordered. So my question is, are there any challenges put forward to you by a disordered system in your ongoing research?
To begin with, I am under pension already for 11 years. So my ongoing research is rather not too experimental. So let's put it this way. So we came across these disordered particles, but we were not looking for them, actually. We were more interested in ordered systems. But from the point of view of XMCD, I have mentioned that the information we get is per atom. Per atom. So from the point of view of XMCD, it's not so important unless you can play around with the angle measurements, or you can somehow select a number of particles and orient them some way. Another thing is if we speak about XRs, for example, then indeed the XRs technique will give you information on the disorder. We have done that also, but it's not part of this talk.
Thank you very much.
Please.
The next question is from Yuri Naiduk.
Thank you. Thank you, Professor Bartolome, for your talk with a lot of results. I would like to ask you about these cobalt particles covered by gold. You said that it appears magnetic moments because of hybridization of orbitals of gold and cobalt, but it is not alloy. It means that this hybridization is only possible at the interface.
That's right. Yeah, only at the
interface. But this interface
there is a change in the surface band. So it has been studied by Storr on other planar layers, and he has shown that because of the different spin orbit coupling of the cobalt and the gold, there is a change in the surface bands with respect to the in-depth bands, and that is why he argues this anisotropy comes from the hybridization between the 3D and 5D. Yeah.
It is also possible if we simply take a thin layer of cobalt and cover it by gold. Without
this has been done. This has been done by Professor Storr before our own work. Yeah.
Thank you very much.
Please. If you allow me, may I try to show you a transparency that I have somewhere? Let me see if I can find it easily. Yeah, here. I think this is the idea. It is in this paper by Storr at JMM volume 200 as a review. And he shows that because of the spin orbit coupling, there is an anisotropy, surface anisotropy provided by the difference between the two magnetic moments, perpendicular and parallel, and that as the band, the gold band connects with the cobalt band, there is a broadening in the bands, and that is what causes the anisotropy. So it is hybridization of the surface cobalt 3D electrons with the conduction bands. So if you are interested in this particular question, I suggest you that you go to the Storr paper, which is experimental and theoretical.
Okay, interesting.
Thank you. If I might ask a simple question, you showed the
questions are never question. Never simple.
Or name. So I'm not an expert, but you showed for permanent magnets example of magnetization behavior, and there were also data points for resistance, I think, on the plot.
No, I don't
For
think I just...
neodymium.
Yeah, this was magnetization measurements in different directions for a parallel field to the Z direction and perpendicular to the Z direction.
Yeah.
Yes, yeah.
And I'm
On the other axis, yeah, it's resistance, yeah. Excuse me.
I'm wondering about the nature of these rapid drops in resistivity, how to explain by simple means. Is there a simple explanation? In the regions of phase transitions, you have these drops in resistivity in both directions.
Of course, the resistivity, the resistivity has got the two sublattice components, but it is mainly due to the iron sublattice. And when there is when there is a structural change which happens here, it is slightly reflected. Is slightly reflected in the resistivity. Actually, we published several papers on the resistivity, which I didn't bring out in this talk because I was centering myself on the XMCD, but I can show you or can send you the references to see how we analyze the resistivity of this neodymium iron boron material. They are not special in this respect, but we did measure them carefully. Also as a function of substitution of the lanthanide with the different rares.
So I see no further questions, or we have. So from Maria, yeah.
Yes. Thank you so much for your interesting presentation, Professor. But I have a question about phthalocyanine. So I saw that you have the complex signal. Yes. So I am wondering how we need to provide information about the magnetic moment, spin and orbital, if we have the composite signal. So it's combination of different valence states, right?
No. It's the magic of this technique. No, we just need to do the integration of the L3 edges, and the sun rules allow to obtain the orbital moment, as I explained. No. We have done the analysis of these peaks, of course, by calculating the different energy levels, and we have explained them. I think they are in this paper. But to get the orbital moment, no, we just have to integrate throughout the edge.
So, and actually you obtain the full orbital moments of the L3H for complex contributions.
For the iron. Remember, we are looking only with XMCD to the element.
Yeah.
So we are just studying the orbital moment of the iron. And since all of them are identical, then is the orbital moment of each. Yeah.
Thank you. But for instance, in iron, sometimes there are different oxidation states. I mean, that's different coordinations, so they can be antiferromagnetically ordered. And in that case, you can't apply probably the SOM rules directly to integrate the XMCD signal, no? Or I can be mistaken.
You are, sorry, you can do it. I think I showed you. Sorry, I'll try to go. Excuse me. To the beginning. Let's see. at the sorry, in my, let's try to get rid of, okay. Can you see my screen?
Yes, sure. Yes.
Okay, here you have got an example where we have in this graph collected systems with iron 0, iron 2, and iron 3. You can see the absorption, and for this absorption, whenever you have a magnetic moment, then in the XMCD you will see the typical peaks.
Octahedral. Yeah.
This it has not to do. I mean, if you have an octahedral case, then the peaks will be different to if you have a tetrahedral case, and then you will be depending whether you are with a metallic state, so that you can speak of bands, or you are in an atomic-like case, like in the phthalocyanide. That is the difference. That is the main difference. In the phthalocyanines, we are right here.
Okay. Okay. Thank you. Thank you so much.
You have not metallic behavior, but atomic-like behavior. And here you will indeed observe differences whether the iron is in an octahedral environment or not. But from the point of view of orbital moment, no. You just need to integrate here.
Okay. Thank you.
Okay.
I see one more question from Yuri Naiduk.
Okay, I have no question. I don't see any questions. Therefore, I would like to say to Professor Bartolome, thanks at first for this your report today, and especially I would like to thank Professor Bartolome from editorial board of the journal Физика низких температур or Low Temperature Physics Journal. Some members of the editorial board are present here, that he helped us and presented his and your colleagues' results in some special issue of journal Физика низких температур. And we hope for further collaboration with Professor Bartolome and received your nice paper in our journal.
Well, thank you, and we shall speak on the details later on, as we have done previously with my previous articles together with Valentina Sirenko, with whom I have a very fine collaboration. Indeed, thank you very much.
Good.
And it was a great honor to participate in this seminar, which I have been following lately in previous cases. Very interesting seminar, very, very interesting.
Thank you for wonderful talk and informative answers. And so thank you very much for your contribution to our series.
Dziękuję.
Gracias.
Okay. Good day.
Thanks everyone, and see you next seminar. Bye-bye.
Thank you.
Bye.
Thank you. Bye-bye.
Bye-bye, Valentina.